Hello, welcome to ECO-595. So in this lecture, we're gonna go over chapter 23. It's basically a chapter about regression. So let's get started. Now I want to use an example to kind of motivate the reason of using regression analysis. So here's an example about bringing your work to home or bringing your home to work. For people who are working and have a family, usually we find there's this work-family conflict. That is, sometimes you have to bring your work to home. That is, just by looking at the picture, you might need to work on something even after you get home during dinner or during weekends. Or sometimes you have to bring your home to work. That means while during the regular working hours, you're gonna need to um, take care of a few things related to the family or related to the kids, things like that. Suppose there are researchers who want to look into this issue and identify what kind of family characteristics can contribute or are related to the tendency to bring your work to home. And apparently, you want to kind of explore the relationship between people's tendency to bring your work to home and the kind of family they have, the kind of person they have, or the kind of job they have. Now, we are looking at a situation where we have more than one variables. The variable number one is whether you bring your work to home, and other variables include the family characteristics, which we usually call the independent variables in regression study, and which can be related to bring work to home, which we call a dependent variable. In this situation, the best way to explore the relationship is really to run a regression where we use bring work to home as the dependent variable and see how all other independent variables, that is the family characteristics, can affect the dependent variable. Okay. Here are a few things, basic things about the regression analysis. So typically, we are interested in the relationship between two variables or multiple variables. So at least we should have two variables right here, and we want to examine the relationship between the two variables. And we call such situation the bivariate statistical techniques because you are looking at the relationship between two variables. And among the two variables, we label them differently. We have a dependent variable y and an independent variable x. We will provide more explanation as to how we can determine which variable is y, which variable is x. And we can conduct correlation analysis, that is typically regression analysis for interval or ratio variables. That means your variable needs to have numbers instead of categories. If you have categories or words, then you cannot run regression analysis directly. You have to do something, and which we will cover later on in next chapter. And now when using regression, we can, for the independent variables, we could have categories or intervals. However, as I mentioned, you can't include categorical variables directly. You're going to have to convert them before running regression. So before we go to regression, there's something called correlation coefficient. And this is typically the first step to examine the relationship between two variables. I'm not a big fan of this measure in the sense that if we run regression analysis, we have this measure directly. So there's not much need to talk about this separately. But given that this measure sometimes gives us a easy and first step to look at the relationship between two variables, let me just briefly talk about it. So the correlation coefficient is actually a statistical measure that tells us the covariation or association between two variables. And it's stated to at least interval variables. That just basic means two variables that are numbers, not categories. Okay? So the correlation coefficient ranges from +1 to -1. And values close to positive one or negative one indicate that the correlation is strong. Otherwise, if the correlation coefficient is close to 0, that means the correlation is very weak. Okay. Now, I have no intention of going over this formula, but here's how we calculate correlation coefficient just for your information. Instead, I want to talk about the general idea of correlation coefficient and just give you a few scatter plots to have a visual idea of different kind of correlation coefficients. Okay, let's start from the last scatter plot in each row here. Now for this one, okay, here the correlation coefficient is +1. That means the correlation is perfectly positive. Okay, perfectly positive. That is, if you look at the dots in the scatter plot, all of them follow a straight line absolutely. And that's the situation we have perfect positive correlation. And the opposite is a perfect negative correlation, which is shown in this scatter plot, where the dots are still follow a perfect straight line, although it's downward sloping. Okay, so these are the two situations that we actually don't see in practice. This is because if you have perfect correlation, then that means you can use X, given the value of X, you can predict Y perfectly. Then there's no need for statistical analysis. That is, you don't need to collect data and analyze data because it's perfect prediction, no uncertainty, no statistics. Okay, so usually what is interesting is that we have something that is not perfect. So if you look at the scatter plot, let's start from the first one. Here the correlation coefficient is 0.3. We can tell two things right now. Number one, the correlation is positive because it's 0.3. Number two, the correlation is not very strong because the number is 0.3. It's not very close to +1. And if you look at the scatter plot, you do have a sense of that because the scatter plot, although following a upward trend, is not very concentrated in comparison to the next scatter plot, where you find the correlation coefficient to be +8 and the dots are crowding together and showing a much stronger upward trend. Okay, so in this case, we say the two variables are positive related and the correlation is very strong because it's close to +1. Now, down here, if you look at this one, the scatter plot, the dots are kind of random. I don't, at least in my opinion, I don't see any trend either positive or negative, right? It seems like it's quite random. So in this case, the correlation coefficient is 0 or almost close to 0, and we say there's no correlation. X, Y are not correlated. And the next one, a correlation coefficient is -6. We can tell two things. Number one, variables are negatively related. And number two, we have what we say moderate negative correlation, because although the dots are kind of close to each other, but it's not very tight. So in this case, we don't have very strong correlation. Okay, so these scatter plots just to give you some ideas of different correlation coefficients and how they look like. Now, so far I've mentioned that we use correlation coefficient and regression to examine the relationship between two variables. And it could be a common mistake then that when people look at the relationship between X and Y, since we observe that when X changes, Y will change with it, there's this tendency to say X is causing Y. So I want to warn you here, that is, even though we can find two variables are correlated, you really cannot say one is causing the other to change. The best thing while using just what the regression we learn in this chapter is to say one is related to the other. Whether it's caused by X or not, that depends on something else. We have other techniques to examine the causation relationship. And I have a simple example here, right? And in this case, we will hear the rooster's crow and the rise of the sun well, we will hear the crow and observe the rising of the sun at the same time. So they are correlated. That is, whenever the sun is rising, we typically could hear the roosters crowing. However, that doesn't mean you can declare that the rooster is causing the sun to rise, which definitely doesn't make sense, right? So in this case, we say these two are correlated, but one is not causing the other. Now, I'm going to skip this for right now because it's about correlation metrics. It's basically just looking at the correlation coefficient between two variables and then make it a matrix if we have more than two variables. So an example of that is shown here, where you have different variables and you want to calculate the correlation coefficient for each pair, then put them in this matrix. Again, I'm not spending time on it is because most of the time a multiple linear regression will be more powerful than this correlation matrix. Okay, and together this example is gone because it's related to correlation matrix. Here's what we need to focus: the simple linear regression analysis. Okay, so what is a simple linear regression analysis? It includes several components here. It is a technique that used to measure the correlation coefficient and the relationship between two variables. Okay, and it's called linear regressions because we are fitting a straight line. So the linear is referring to the straight line part, and the simple is referring to the fact that we only have a y and have one x. So one y, one x, that is a situation where we have simple linear regression. All right. And in regression analysis, the basic idea is, let me show you this scatter plot. Okay. So for example, if you look at the first scatter plot, okay, we have x and y, and we're interested in the relationship between x and y, and in particular, maybe we want to use the value of x to predict y. All right. If that's the case, then the basic idea for simple linear regression is, how about, since all the dots are following an upward slope trend, how about we try to fit a straight line that can best represent the relationship between x and y, since we observe an upward trend. So it's not the best drawing, but let me redo it because it's really okay. Right. So how about we use a straight line to kind of represent the relationship in x and y, and meanwhile we want that straight line to be close to all observations so it can best represent the data. Okay, if we can figure out the parameters of the line, then we are able to use that straight line to make any predictions. Given the value of x, we can predict the y. Okay. So to determine the straight line as you learned in your high school or middle school, whichever, you know you're gonna need two items. The first item is a slope. You need to know the slope, and the second item is the y-intercept. If you got those two, you got the straight line. So regression analysis, especially simple linear regression analysis, is just accomplishing what I just mentioned. And here is the regression equation. That is, we let y, the dependent variable, equal to a y-intercept, which is denoted by a, plus a slope denoted by beta times x. Okay, so as of right now, let's just cover this part, okay, because we don't need it yet. And if you look at this equation, I hope you can see through that we are actually representing a straight line using this equation. If that's not the case, then I bet this equation will ring a bell for you. Well, of course, assuming that you learned math in the US. And because, well, I mean, for me, I learned math in China, so our um, education, in our math education, we actually use y equal to a plus bx or something like that. And I learned from my students in the past that here in the US, the math is taught in a way that b is used to denote the y-intercept, m is used to denote the slope. But anyway, I hope you can see the similarity between these two equations. That is, both beta and m are denoting the slope, and alpha there or b here denotes the y-intercept. Okay, and so y is called the dependent variable in the sense that we say we expect y to depend on the value of x, or in other words, when the value of x changes, y will change with it, and we denote that variable as y. We denote x to be the independent variable in the sense that x does not depend on y. Instead, x can affect y. That is, when x changes, y will change with it. Okay, and the most common example you can hear when talking about the relationship between x and y is probably the height and weight situation, right? If you think about person's height versus the person's weight, now apparently a person's height can affect the weight, but the weight, a person's weight will not affect that person's height. So if you think about it, then in between height and weight, y, the dependent variable, will be the weight because weight can be affected by height. And the independent variable x will be height because height is depending on something else, at least not weight. Okay? And as I just mentioned, alpha will be the y-intercept and beta is the slope coefficient. All right. And this is just an illustration of the alpha and beta thing, which I'm sure you learned in your early math education. So I'm going to skip that. And just want to say a few things about the alpha and beta here. So in statistics, although I didn't emphasize this concept a lot in our course, but in statistics, we usually call alpha and beta the population parameters that we need to estimate using the sample data. Well, for right now, what you need to understand is that, well, if I give you the data, you can't get alpha and beta automatically, right? If I give you the scatter plot, just like the one we saw a moment ago, oops. Okay, so if I give you the data for the first scatter plot, right, you won't be able to tell alpha or beta. You can't tell the position of this line, and you can't tell alpha and beta directly. So we do need some technique to estimate alpha and beta using the data. Okay, and then once we are able to do that, which we'll talk in a minute, we will be able to use beta to examine the strength and direction of the relationship between the two variables. After all, the purpose of estimating regression is two things. Number one, we want to know the relationship between two variables. Number two, we want to make some predictions. So beta will become the key factor there. Okay. All right, so I want to kind of give you an idea how we run regression analysis using this very simple example here. So what we have is the annual bonuses in $1,000 of 6 employees with different years of experience, okay? And we also have data on the number of years of experience, right? So we have two variables, and apparently we can tell bonus should be the dependent variable y because bonus depends on experience, and experience should be the independent variable x. And we have 6 observations here. Now the numbers are a little bit off, so you should read it as for this first observation, we have someone worked for 1 year, got $6,000 as bonus, 2 years, 1,000, 3 years, 9,000, etc. Okay, and notice that the bonus are measured in thousands of dollars. All right, so that's the setting. And what we want right now is a straight line, okay, that can denote the relationship between two variables. Well, as a start point, we usually look at the scatter plot for the data. So here's the one for our example, okay? So we have 6 observations denoted by the 6 dots here, and we do observe an upward trend, right, somewhere. Now the question is, how do we get that straight line? All right, so I can draw one line, probably somewhere there, right? In the middle, I mean, in between the observations, not going through any one of them, it's kind of close to the observation. Or another option is maybe, you know, since 2 dots determine a line, right, I can draw a line going through these 2 observations and still kind of close to the observations. Or draw a line like this going through these 2, right? So the question becomes, which line should we adopt, right? Which line will give us the best practical solution or the best practical results? Now, if we're gonna use the straight line to make further predictions, if we have someone work for example, 5 years, we want to predict his or her bonus, which line should we use? Okay, so the answer really lies in a technique called ordinary least squares method. Okay, and this is a commonly used method, at least for the basic regression analysis, whether you have simple linear regression or multiple linear regression. Right. So actually, this is my purpose of introducing simple linear regression, is that I want to give you a general idea as to what ordinary least squares method is about and how we apply it and what it can give us. Okay, and I do want to go into a little bit details because I'm sure you're gonna learn regression analysis in a stat course in the future, and I'm sure your professor will talk about this method, but sometimes due to time limit, they may not be able to go into details, and also this method is not very it's not that easy to understand, at least at the beginning. So I want to take this opportunity to introduce you to the idea of least squares method. What's going on here? Well, so again, we use the blue dots to represent the 6 observations, and we've determined the best line, which is denoted by the red line here. So how do we determine that? It turns out of all the possible straight lines on the graph, the best one is the line that has the shortest distance from the observation to the line. Okay, so that means I have different lines, okay, on the graph. Let me show you back here. So I have these 3 lines back here, right? And I'm trying to determine which one is the best, or even there's another one that's better. So it turns out the best line is that if you draw a vertical distance from the observation to the line you're fitting, okay, that's a vertical distance. And right now I'm trying to fit this line. I want to draw one more time just to, okay. And for this observation, I want to draw a vertical distance from the observation to the line. And same for the next one, same for the rest. Okay. If all of these vertical distances are minimized, then the line is the best. So if you go back to the method, at least now the least part makes sense because we want to minimize the vertical distance from the observation to our fitted line. Okay. So what about the squares? Where does that come from? Okay. Well, let's think about it. We want to minimize vertical distance, all of them. Okay, how can we achieve that? One simple idea is, well, what if we add all the vertical distances up, all the straight line up here, and then minimize the total? Well, typically that would work because if the total is minimized, then individually they would minimize. Except that you have positive numbers and negative numbers. If that's the case, then the idea that doesn't work, okay? So for example, starting from the first observation here, if you calculate the vertical distance from this observation to the line, you're gonna use probably 6 minus something like 3, I would think, right? And you got a vertical distance of 3, positive 3 here, okay? Then for this vertical distance, you're gonna need to follow the same idea. That is, you go from the observation, which is about 1, to the line, which is about 4.5, I think. So you're gonna use 1 minus 4.5, which will give you a negative number, negative 5.5, 4.5, I think. It's a rough calculation, just to illustrate what's going on, right? So I have positive 3, negative 4.5, and another positive 1 for this observation, another negative 1 for that observation. So if you go through the vertical distances, you're going to have positive 1, 3 of them, and negative 1, 3 of them. Now, if you add them together, right, the positive and negative will cancel out. So even if the eventual answer is minimized, the total is minimized, it's not a guarantee that each of these will be minimized. All right, and that's where the squares come from. So an idea to go around this is that you square the distances. So positive 3 squared turns to be 9, and negative 4.5 squared is around 17 something. Apparently, I'm not good at that. 4.5 times 4.5. Oops. 20. Oops. I'm not sure what's going on. So if you square that, you will get positive 20.25, okay? And keep going for the rest of the vertical distances. Now, after squaring each vertical distance, if you add the squares up and minimize the total of the squares, you will get each vertical distance minimized. And that's where the squares come from, okay? So we are squaring the distances from the observation to our fitted line and then minimize the total of the squares. If that's achieved, then we got the best line. Okay. All right. In case you wonder, usually I don't expect you to do so, but in case you wonder, well, if I don't know where the line is in the first place, how can I calculate the vertical distance? Well, don't worry about it. We have something called calculus derivatives. That's something needed to kind of calculate or find out this straight line, right? So let's put that aside, because after all, my goal here is not to let you know how we calculate or how we really go through the calculation and get the straight line. Okay, my goal is to introduce you to the idea of least squares method. Least means we're minimizing the vertical distances, and squares means we are squaring the distance first, then minimize the total of the squares. Okay. And then once we use the method described and find the straight line, right, we will denote that as y hat equal to a plus bx. I just want to mention briefly, the reason we change from alpha to beta is because, as I mentioned, alpha and beta needs to be estimated using data. Now, if we actually use the data and estimate the straight line, like what we have here, y hat is equal to 0.934 plus 2.114, then the 0.934 part is denoted by A, and the 2.114 part is denoted by B, not alpha and beta anymore. Okay, alpha and beta need to be estimated, but once you use the data, do the estimation, it becomes denoted by A and B. Same for Y. You might notice that we have Y hat instead of Y. Most of the time, I'm sorry, not most of the time, there are times when people just ignore it and just use Y, but strictly speaking, that is not correct because this Y hat is our prediction. That is, if I give you a y of x, you plugging into this equation, you will be able to predict y, but that's not the actual y, okay? For example, just to illustrate the difference. We have someone from the data worked for 1 year and the bonus is $6,000, right? That's the actual y. This is the actual bonus for this person. But if we have another person and we're trying to predict his bonus after working for 1 year, we wouldn't predict that it's $6,000 because that's just one observation from a person. That's not accurate, okay? And what we could do is to plug in the straight line we have here, okay? And so what we have will be equal to, if we're gonna do the prediction, 0.934 plus 2.114 multiplied by 1, which is equal to, let me go through the calculation quickly. $3.048. Okay, so if we have one person for 1 year and we predict his bonus, it will be $3,000, not $6,000 as the one observation we saw in the data. And this 3.048 or $3,000 is the predicted bonus for that person who worked from 1 year. So that's why we denote it by y hat, is not the y. Okay. All right. That's the kind of the basic introduction for regression. Okay. So in order for you to work on something practically, okay, I bring this car dealer example, and I will also show you how to run regression using Excel. And you, after learning chapter 24, which is multiple linear regression, you will be asked to work on the data analysis project in which you're gonna do two parts. Number one will be time series analysis, and number two will be multiple linear regression analysis. Okay, so let's look at the car dealership example. Car dealers across North America use the Red Book to help them determine the value of used cars that their customers trade in when purchasing new cars. The book, which is published monthly, lists the trade-in values for all basic models of the car. It provides alternative values for each car model according to its condition and optional features. The values are determined on the basis of the average paid at recent used car auctions, the source of supply for many used car dealers. However, the Red Book does not indicate the value determined by the odometer reading, despite the fact that a critical factor for used car buyers is how far the car has been driven. To examine this issue, a used car dealer randomly selected 100 3-year-old Toyota Camrys that were sold at auction during the past month. The dealer recorded the price in $1,000 and the number of miles in thousand on the odometer. The dealer wants to find the regression line. So that's the question. Okay, let's think about what we have here. So we have two variables, okay? The first variable is the price of the used car, and the second variable is the mileage on the car. Now, apparently, price of the car should be the dependent variable, y, and number of miles on the odometer should be the independent variable, x. Mileage affects price, price doesn't affect mileage, right? So that's the situation. Now, in the next lecture So I'm gonna show you how to run the regression using Excel and continue with the example. So I'll see you next time.